Linear approximations day one. A linear approximation is used to replace a complicated formula with a simpler one over an interval of values. There are a variety of different ways to do this. The thing we're going to focus on today is called linearization. The equation of the tangent line is the linearization. So basically, linearization is just a fancy word for the equation of the tangent line when written in y equals tangent line form. So we want to write it basically as a function. We are assuming that that tangent line has a very close approximation of that function. Essentially, what we're saying is that every function that is continuous is locally linear. So what that means is in a very small range of x values around a certain point and a very small range of y values around that certain point, we can assume that the function is linear. So if we zoomed in really, really, really far on the function right around here, even though the function is curved as you zoom out, when you zoom in, it looks like it's linear as you get closer and closer and closer to it. And we'll show that on Desmos as we do a couple problems. Basically, we start with the point slope form equation and we do a bunch of replacing. So instead of x1, we put a, because we're just assuming that we're going to substitute in values at a. We replace y1 with the function value at a. So these are x and y values, a comma f of a. And then the slope is the derivative. And so we end up with this, and then we add the f of a over to the right side. Don't get too confused. It looks like there's a lot of stuff going on, but it's basically just the equation of the tangent line where you add the y value over to the other side. That's all it is. Equation of tangent line. So what we're going to do is we're going to find some linearizations right now. First thing we want to do is, since we know that it's at x equals 0, we need to find the value of the function at x equals 0. So sine of 0 is 0. Now we'll take the derivative, so f prime of x is cosine of x. And what we're going to do is we're going to substitute 0 in there. So cosine of 0 is 1. Now we have all the information that we need. So we would say y minus y1 equals m times x minus x1. So y minus 0 equals 1 times x minus 0. So we get y equals x. If this 0 over here was not a 0, we would have to add it to the other side. This is our linearization. And so since that's our linearization, that is really all we need to know. So if we graph sine of x, if we graph our linearization should look something like that. So that's the equation of the tangent line at x equals 0. It's the line y equals x. Notice that if I zoomed in really, really, really close, for some values of x, it's going to look very much like the equation of the graph. Number 2, f of x equals cosine x. Y minus 1 equals 0 times x minus 0. When we solve, we get y equals 1. This should make sense, since if we graph cosine, we end up with a horizontal tangent line at 1. Once again, if we zoom in, it ends up being locally linear. So that equation of the line y equals 1 looks really, really, really close to the function at those values. We're going to go to Desmos and kind of explore this a little bit more. Here's what goes on with the sine of x. So notice at 0, we have that tangent line, and that tangent line is y equals x. I'm going to zoom in on it. What you can see is that for values that are pretty close, looks like between negative zero point 0.5 and zero point 0.5, this equation models the function pretty well. At 0, it's exactly the same, and everywhere else it's off by just a little bit. Now, why might we want to use a linearization? Well, let's say we wanted to find the value of sine of zero point 0.5, and you don't have a calculator. Sine of zero point 0.5 is not very easy to do without a calculator. Zero point 0.5 is not something that's very easy to get in terms of it's not a, a value in terms of pi or anything like that. So if we're looking at this, um, your linearization is going to be sine of zero point 0.5 is approximately 0 0.5. The value of the actual function there is 0.4794. Now, while that's off by a little bit, um, it's at least a pretty decent approximation for us if we don't have a calculator. One thing to notice, though, is that as you get further and further away from the point that you made your linearization, you get further and further away from a good answer. So if I wanted to find the sine of 3, uh, obviously sine of pi is 0, but if I wanted to find the sine of 3, that's about 0.141. My linearization is 3. That's a terrible approximation. If I wanted to find the sine of 3 and I didn't have a calculator and I wanted something that was a good approximation, what I should do is I should make my linearization somewhere near 3. So a suggestion maybe might be to make it at pi, because I know exactly how to make the linearization at pi. That would be y minus pi equals, the derivative is cosine, and cosine of pi is -1. So notice that my slope is going to be -1. My intersection point's at pi comma 0. So what I end up with is y equals -1x plus pi. And I can substitute values in there, and I can get a pretty decent approximation. So the function value at 3 is 0.14112. And the value of the linearization is 0.1416. That's really, really, really close. And so linearizations are good for approximating things. Once again, notice that this linearization that we just made is very good for values around pi, and 3 is a value around pi, but it's not very good for values that go further and further away. So it ends up being pretty good for a while, but then not so good after that. And I could have done the same thing for cosine or whatever. Find the linearization of f of x equals cosine of x at pi over 2. So now this is another similar situation. So our linearization is y minus 0 equals -1 times x minus pi over 2. So what I end up with is y equals -x plus pi over 2. That's our linearization. Sketching the graph and the linearization, I will do that on Desmos. And what we see is we have a linearization that is y equals -x plus pi over 2. It intersects there, and we can find good approximations around x equals pi over 2. But again, as we get further away, our linearization gets worse and worse. So we're going to find the linearization for f of x equals 1 plus x to the k at x equals 0. Just a reminder of what we're doing. We're finding the equation of the tangent line, which we could substitute in f of x's and f of a, like a with that point where we're centering it around. And then we typically write linearizations with the y value on one side and everything else on the other side. So we're going to find out what happens. So at f of 0, we get 1. because it doesn't really matter what k is in this problem. If you put 0 in, you get 1 to the k, which is k. Also, in this problem, k represents a variable of some sort. So what we're doing is we're trying to figure out what happens in general when we have this exponent in this 1 to the x situation. So what we're going to do here is we're going to then take the derivative of this function. So f prime of x equals k times 1 plus x to the k minus 1. Remember, we're treating k like it's a constant. We just don't know what the constant is at this point. And now if we take f prime of 0, we get k times 1 plus x to the k minus 1. Well, since we put 0 in, it's 1 to the k minus 1. It still doesn't matter what it is. So f prime of 0 is always k. So if we rewrite this as a linearization, we get f of x, or y, equals 1 plus k times x minus 0. So we get y equals kx plus 1, or 1 plus kx. At the end of this video, I'll explain to you why, when the textbook writes linearization, they write it with this f of a in front instead of at the end like we would typically write it. I'll show you it's kind of leading to something as we move along that you'll get to in about chapter 9. But if we take a look at 1 plus x to the k power, let's say k is 2. If we have a quadratic, notice that the slope of this line, this 1 plus kx, we have a slope of 2. If we move that to 3, notice that our linearization still has a plus 1, it still has a y-intercept of 1, but now our slope is 3, and you can see that pretty clearly from the graph. If we move it to 4, it still has a y-intercept of 1, but the slope is 4. So that k is obviously dependent. The k then dictates what the slope of our linearization is. Use a linear approximation to approximate 0.9 to the 3 halves. So now what we can do is we can use this linearization. We know what k is in this case. K is 3 halves. So because of that, we're going to use y equals 1 plus 3 halves x, and we're going to approximate 0.9 to the 3 halves. This is a good example of when we would use linearization. 0.9 to the 3 halves is no fun to try and do by hand if you don't have a calculator. 0.9 is really close to 1. And what we have here is 1 plus some value of x. So essentially what we're doing right now is we're saying that x equals negative 0.1, or x equals negative 1/10. And that's really close to this x equals 0 that we were centering this thing around. Remember, we were centering this around x equals 0. So what we can do now is we can put x equals negative 1/10 in. So 1 plus 3 halves times negative 1/10 will give us 1 minus 3/20. So our approximation for this, we approximate this to be 17/20, or 0.85. That's our approximation. So on Desmos, I changed k to be 3 halves. And now what I want to do is I want to find negative 0.1. And the reason why I want to find negative 0.1 is because if I substitute in negative 0.1 for x, that's actually 0.9 to the 3 halves. So in our original function, it's about 0.854. And that's not going to be very fun to actually calculate. Our approximation was 0.85. Those are really close. It's probably close enough for most approximation work that you would want to do with something like this, and that ends up being good. One thing that we have to be aware of, though, and I know I've said this, is your approximation gets a lot worse as you move further along. So if I wanted to approximate, for example, 3 to the 3 halves, this would be a horrible approximation technique because I would substitute 2 in and I would get 4. However, the actual value of 3 to the 3/2 is up around 5. So we get way off way fast. And as you zoom further out, clearly it gets much worse as you go along. Now what we have to do is we want to use L of x, this linear approximation, for root 1 plus x to approximate 4.1. That's going to be the same thing as k to the 1/2. I want you to try this for a and b, and then we'll be back. So after you use the approximation, remember that we know that k is going to be 1/2 here. We get about 2.55 as our approximation, and that's not really all that close to the square root of 4.1. So if we look at this on Desmos real fast, uh, we see that if we put in 3.1 to our function, we get 2.025. There's a pretty significant gap between our linearization and this. So that's just another reason to make sure that we're careful around where we're centering it. Our function, if we zoom in real far, it's pretty good for a while, but it gets off pretty fast. Also notice that if we zoom in far enough, our function doesn't look any different than a line. So even though we know our function is curved, the farther we zoom in, the more it looks like a line. One of the reasons why I wanted to emphasize why they put f of a in front is as we move along, we won't only have things like linearizations, but we'll also have things like quadraticizations, cubiциzations, quarticizations of functions. And I know those aren't the words that we're actually going to use later, but what ends up happening is the more derivatives we take, we can approximate functions more and more accurately as we get along. So linearization is pretty accurate for a very short period of time. And then a quadraticization, I know I'm using a made up word, but they get more and more accurate as we get along. And you can also center them at a variety of different points. So anywhere they are centered around this function, you get pretty good approximations around the center, but then obviously they get worse and worse uh, as you move along from the original function. And we can do this for a variety of different functions. So like we already showed, we can do a linearization at sine, which is good around wherever our center is. But then our quadratic and cubic and quartic, and we can go much, much further approximations. They end up doing a very good job in the general area around the function. But then as you get further away, they become much worse, clearly. So that is basically why we stress linearization, because later on it ends up becoming very, very important. And we spend entire chapters on it.